All right, kinetic molecular theory. So when we talk about the kinetic molecular theory, the first thing we need to do is we need to realize that when we talk about the kinetic molecular theory, or KMT for short, we're talking about gases. We're talking about gases that are considered to be what we would call ideal gases. What does that mean to be an ideal gas? Well, what it means is these are gases that are acting in perfect conditions, meaning we have true STP, or we end up with conditions such as high temperatures and very low pressures, so that a real gas can simulate an ideal gas. Okay? So this kinetic molecular theory idea applies to gases like in a perfect world. What I'm going to do is on page 9 in your packets, you are asked a number of things about kinetic molecular theory. And basically what it does is it gives some properties about how gases act if they were considered to be ideal. So here we go. Let's start with number 1. Number 1 says, name the postulates of the kinetic molecular theory and state whether or not you believe they do a good job of describing how real gases work. So here we go. The first one that I would say is this. And you're going to need to write small. Gases are in constant random motion. So you know what I think about when I think about, I have kids, okay, but if you've ever, gone to like Jungle Java, or gone to like these just go watch the playground by the school, right? You're going to see a whole lot of kids that are in constant random motion. Well, now I want you to pretend you gave each of them like 3 candy bars, and then watch the constant random motion that would occur. All right, they'd be all over each other, bouncing all over the place, be running here to there, etc. And is this how gases really do function? Yeah, it's a pretty good indicator of atomic structure and atomic function with regards to gases. So that's the first one. It's pretty accurate. Number 2, that the kinetic energy of a gas is proportionate to temperature. Here's what I mean by that. If you increase the temperature, the gas particles, this constant random motion, they move faster. And likewise, if I decrease the temperature, they move slower. To me, that just makes sense, like human beings, right? If you took and put my feet on burning hot coals, I'm going to move, right? So you increase the temperature, my kinetic energy, my energy of motion is going to increase. So, does this one talk about gases? Yeah, it does, and it's pretty accurate. Number 3, gas molecules have small volumes. They're tiny. Yeah, they're little. They're small volumes. Again, pretty accurate. Next one. Gas molecules in an ideal setting don't interact. Well, I'm not in love with that one, okay? And the reason that I would tell you I'm not in love, it depends on the gas. Sometimes there can be good assumptions for this, and sometimes there can't be, right? For example, like water vapor is going to interact a lot more than helium gas, things that are in the noble gas family. Yeah, they're not going to interact very much. They got 8 electrons, and they're going to do their own thing. But something like water vapor, yeah, that'll react and interact with other molecules. And so, the reason I really don't like that either is this. So we talked about here that in an ideal kinetic molecular theory setting, gas molecules don't really interact. But this last one says this, that pressure results from the interaction, or specifically the collision of gas molecules with each other. And guys, boys, that's a big deal, right? I mean, we have these, you go get your car worked on. We have these huge hydraulic presses that take your car, this multi-ton thing, and raise it up off the ground, right? It could be, 3,000 pounds of car being raised. Why? What are we using? We're using water vapor pressure. So the pressure buildup in that piston is due to the collision of these gas molecules. So we can harness it and we can use that energy. Does that describe gases and how they really interact? Yeah. Now, this is more of like a definition than an assumption, but I like the idea that pressure results from it. So question number 2 on your thing says this. It says, based on the postulates of the kinetic molecular theory, give conditions of pressure and temperature you believe would cause a real gas to best simulate an ideal gas. Well, what you'd be looking for is high temperatures and low pressures. High temperatures, low pressures for number 2. Number 3 says, Avogadro's law states the volume of the gas is directly proportional to the number of moles of the gas, but has nothing to do with the identity. Is this correct? Well, when I think about that, I think about this. Of course that's correct. If I take a piston, like I was just talking about, and I put gas molecules in it, and I only put a few in this one, versus taking and putting, a whole bunch of gas molecules in this one. Well, the pressure that is going to be derived from this particular system is going to be significantly more. And when we were to measure, Avogadro talks about this mole thing, right? So if we were to count and look at these particles and compare it, of course there would be more moles of gas here than there would be here. So Avogadro's law would definitely be intact. Okay? Now, one of the reasons that this question is asking us about is it also is making us realize that ideal gases, they don't really have a volume. Okay? They're really, really tiny. They have a volume, but we really can't measure it. And so the size of the molecule doesn't really matter. But because ideal gases don't interact with each other, there's no forces. As a result, ideal gas molecules do behave according to Avogadro's law. Okay, and that's what I'm trying to get across here. Number 4 says, nowadays we have a better idea of how gases behave than when the gas laws were first introduced. And yeah, just technologies have made that possible for us. Explain why we continue to use these laws even though we can get better answers with the information we have. And the best reason that I could tell you is it gives us ways in which we can take pressures, volumes, and temperatures and compare them to one another. So we still use Boyle's, Charles, and Gay-Lussac's laws, even though we've come up with even better ways to measure them in the common world that we live in today. So number 4 would say, they do a pretty good job of it.